The world you live in is hanging by a silken thread of silicon, a thread just nanometers wide, and yet we have built our entire civilization upon its fragile back. We are told that our modern, hyper-automated factories are the pinnacle of human achievement. But the truth is far more cynical. They are monuments to a global supply chain that could vanish in a single afternoon. Therefore, when the digital lights go out and the chips stop talking, only one machine will remain standing to rebuild the order of the world. You are looking at the Monarch 10EE, not just a piece of vintage iron, but a civilizational insurance policy that doesn't require a cloud connection to function. The concept of industrial survivalism, frequently termed in technical literature as technical prepping, represents a sophisticated evolution of the instinct for preservation, shifting the focus from individual biological survival to the maintenance of a society's actual productive capacity. At the heart of this philosophy lies a fundamental and sobering thesis. Our contemporary technological infrastructure, while characterized by efficiency without precedent, is structurally brittle due to its absolute dependence on global supply chains, high-density semiconductors, and proprietary software ecosystems. In a scenario of systemic collapse, triggered by a high-altitude electromagnetic pulse, prolonged cyber warfare, or a catastrophic rupture of the just-in-time logistics model, the technical prepping thesis posits that manual machines, exemplified by the iconic Monarch 10EE lathe, will be the only means of production capable of sustaining the reconstruction of social order. We have transitioned from manual manufacturing to computer numerical control, or CNC, over recent decades, a move hailed as the peak of precision. But from a strategic resilience standpoint, this transition introduced a terminal vulnerability. While manual machines operate through direct physical linkages between the operator and the tool, modern systems interpose layers of digital abstraction. These layers rely on chips manufactured almost exclusively in regions of the world that are geopolitically unstable. The idea that manual machines are the only ones that will remain is not merely a nostalgic longing. It is grounded in the understanding that complexity is an enemy of robustness under extreme stress. A modern CNC system is the final node of an invisible network, including cloud-based software licensing, microprocessors sensitive to thermal variations, and electronic sensors that cannot be repaired in a traditional machine shop. In contrast, industrial survivalism values tools possessing mechanical transparency, a state where every failure can be visually diagnosed and repaired through the manual fabrication of replacement components. To perform a forensic analysis of our dependence, we must look at the anatomy of technological failure. The reliance on chips and software updates creates a single point of failure that acts as a kill switch for modern industry. Most modern industrial controllers use metal oxide semiconductor devices that operate at extremely low voltages, making them vulnerable to permanent damage from even minimal electrical transients. In a collapse scenario, the inability to obtain a replacement chip or validate a software license via servers that are now offline would transform billion-dollar industrial parks into monuments of immobile scrap. For the technical prepper, the manual machine is a civilizational life insurance policy. This becomes evident when analyzing the mechanism of a high-altitude electromagnetic pulse, or HEMP. This phenomenon, generated by stratospheric nuclear detonations or solar storms, produces a surge of electromagnetic energy that induces massive currents that destroy sensitive electronics. The science behind the vulnerability of digital systems resides in the physics of semiconductor materials. Gamma rays from a nuclear explosion interact with air molecules to produce recoil electrons, known as Compton electrons. This energy pulse travels at the speed of light and can permanently disable continental-scale power grids. For modern industrial systems, the danger is twofold. Front door, coupling through antennas and communication cables that carry transients directly to processors, and back door, coupling through the machine's own frame or power cables, which act as antennas to capture EMP energy. Modern chips, with their nanometric scale traces, lack the thermal mass to dissipate the heat generated by these induced currents, resulting in microscopic holes in the transistor gate insulation, a catastrophic failure known as gate breakdown. It is within this context that the Monarch 10EE, particularly versions utilizing the works-in-a-drawer system, gains a status that is almost mystical. Unlike modern transistors, the vacuum tubes used in the 10EE's motor control operate through the emission of electrons in a vacuum between robust metal electrodes. They are inherently capable of withstanding voltage spikes that would instantly evaporate a modern semiconductor. While this system was eventually replaced by solid-state modular systems in the 1960s to increase peacetime reliability, the industrial survivalist prefers the tube architecture due to its resistance to transients and the ease of visual diagnosis. A burnt tube can often be identified simply because it is no longer glowing. The Monarch 10EE is the gold standard of toolroom machinery. Introduced in 1939, it was designed for extreme precision in a compact size, capable of maintaining tolerances of 0.001 inches over decades of use. The physical robustness of the machine is a product of its metallurgy. The 10EE construction utilizes a proprietary high-strength cast iron alloy known as Monarch metal, and its bedways are flame-hardened to resist wear. This is crucial in a survival scenario where preventive maintenance is limited and replacement of the entire machine is impossible. The 10EE's precision allows it to function as a mother machine. In an industrial collapse, the capacity to manufacture high-precision components for other machines, such as spindles for milling machines, fuel injectors for diesel engines, or surgical instruments, becomes the basis for restoring functional technology. The 10EE is valued because it can produce parts with a finish and accuracy that eliminate the need for subsequent grinding operations, which require even more specialized and vulnerable machinery. However, not all Monarch 10EEs are equal in the eyes of the survivalist, as the choice of drive system is a critical decision based on the expected level of technological collapse. The motor generator system is the preferred choice for a total collapse scenario. It uses an AC motor to physically drive a DC generator, which in turn powers the lathe's traction motor. This is a purely electromechanical system with no electronics to fail. It can be repaired by rewinding copper windings and replacing carbon brushes, skills that can be executed with rudimentary materials. The Ward-Leonard field excitation circuit found in these units is a masterclass in kinetic control. In this setup, the AC motor spins at a constant rate, driving the main DC generator and a smaller exciter generator. The exciter provides a stable DC current used to energize the field windings of both the main generator and the final drive motor. By using a heavy-duty rheostat to vary the current in the main generator's field, the operator controls the magnetic flux, which directly dictates the voltage output of the generator without needing to change the physical speed of the AC motor. This high-voltage DC is then fed to the armature of the drive motor. For ultra-low speeds with high torque, the circuit employs field weakening on the drive motor itself. By reducing the field current in the motor while maintaining high voltage to the armature, the motor is forced to spin faster, or conversely, by strengthening the field at low armature voltages, it produces massive, unstoppable torque for heavy initial cuts. This loop is entirely analog, entirely transparent, and entirely repairable, with a spool of copper wire and a basic understanding of Ohm's law. By contrast, the works-in-a-drawer system uses giant gas-filled or mercury thermotrons to rectify current. It offers superb speed control and high EMP resistance, though it requires a stockpile of replacement tubes which are no longer manufactured on a large scale. The modular drive systems using primitive solid-state components are the most vulnerable to electromagnetic pulses and the hardest to repair without access to period-specific semiconductors. Even the most perfect machine is useless if it cannot be lubricated, and a precision machine like the Monarch 10EE will be destroyed in weeks without proper lubrication. In a post-crisis scenario, high-tech mineral oils and complex lithium greases will vanish quickly from shelves. Efficient lubrication must reduce friction, dissipate heat, and prevent corrosion. In manual machines, contamination by dust, moisture, and metal debris is the primary challenge. Without modern detergent and dispersant additives, residues will accumulate in the lathe's ways, acting as an abrasive paste that destroys the machine's precision. Technical analysis indicates that lubrication management must change from a change and discard model to a local refining and regeneration model. Gravity filtration systems and sediment tanks can allow oil to be reused multiple times, provided viscosity is monitored manually through simple fluidity tests. Research into emergency substitutes reveals that vegetable oils and animal fats were the primary lubricants of the Industrial Revolution and can be successfully reemployed. Oils such as soybean, olive, and rapeseed possess a natural lubricity that often exceeds pure mineral oils due to the strong polarity of triglyceride molecules that adhere to metal surfaces. But these oils suffer from low oxidative stability. If left in the machine, they react with oxygen and polymerize, becoming a sticky varnish-like substance that can seize components. The industrial survivalist must master basic chemistry to add natural antioxidants, such as vitamin E, extracted from seeds, or perform partial hydrogenation to stabilize these oils. To produce greases for low-speed bearings, one can manufacture metallic soaps by reacting animal fat with hydrated lime to create a calcium soap. The process of refining these biolubricants through titration is a mandatory skill for the technical prepper. You begin by measuring the free fatty acid content of your raw oil. This involves taking a 10 milliliter sample of oil and dissolving it in isopropyl alcohol, then adding a phenolphthalein indicator. You then slowly drip a 0.1% lye solution into the mixture until it turns a faint pink, which indicates neutralization. The amount of lye used tells you exactly how much sodium hydroxide or potassium hydroxide you must add to your main batch to wash the oil. Heating the main batch to 55 degrees Celsius, 131 degrees Fahrenheit, and mixing in the calculated lye solution triggers saponification of the free fatty acids, which then settle to the bottom as soap stock. After a water wash to remove residual lye, you are left with a neutral, high lubricity oil that won't corrode your 10EE's precision surfaces. For the final stage of stabilization, you can introduce natural tocopherols, or vitamin E, at a concentration of 500 parts per million, which interrupts the free radical chain reaction of oxidation, preventing the oil from turning into a gummy varnish during long periods of machine idleness. The technical depth of survival manufacturing extends to the tools themselves, as a Monarch 10EE without a cutting tool is merely a motor spinning a piece of metal. Modern manufacturing depends on carbide inserts coated with ceramics via chemical vapor deposition, tools impossible to manufacture without high-tech infrastructure. For the technical prepper, the secret to survival lies in high-speed steel and high-carbon steels. Unlike carbide, HSS can be forged, annealed, shaped by grinding, and heat-treated in a common forge. Recycled steels from automotive components, such as crankshafts, connecting rods, and truck springs, can be transformed into effective cutting tools if precise heat treatment cycles are followed. Research demonstrates it is possible to raise the carbon content of scrap steel through box carburizing. By packing low-carbon scrap into a sealed box with pulverized charcoal and a catalyst like barium carbonate, and heating it to approximately 925 degrees Celsius, 1700 degrees Fahrenheit, for several hours, carbon atoms migrate into the surface of the metal. This process allows the core of the tool to remain tough, while the surface becomes hard enough to cut softer metals. To produce durable cutting tools from such scrap, the survivalist ignores modern conveniences and focuses on basic thermal physics. This involves normalizing the steel to relieve internal stresses, hardening it by heating to the critical point, where it becomes non-magnetic, followed by quenching in oil and finally tempering to remove brittleness. Expansion of this DIY recycling process requires identifying specific donor alloys from the industrial wasteland. Truck leaf springs are typically made of 5160 alloy steel, which contains chromium for deep hardening and manganese for toughness. This is an ideal material for making scrapers and heavy-duty cutters. Old files and chisels are often 1095 high-carbon steel, which can be reforged into fine precision cutters for the 10EE. For the box carburizing process, the pack should ideally consist of 80% pulverized charcoal and 20% barium carbonate as an energizer. The part must be sealed in a pipe or box with this mixture using fire clay to prevent oxygen from entering, which would cause decarburization. The soak time at temperature determines the depth of the carbon case. A rule of thumb is 0.006 inches of case depth per hour at 925 degrees Celsius. After the soak, the box is allowed to cool, and the part is then removed for a second heating to the hardening temperature and an oil quench. The final and most critical step is tempering, which is guided by the spectrum of oxidation colors. This is the visual language of the survivalist blacksmith. As the cleaned and polished steel is gently reheated, an oxide film grows, changing color with the temperature. To master the 10EE's toolroom, one must memorize the scale. Pale straw at 220 degrees Celsius, 430 degrees Fahrenheit, for turning tools where extreme hardness is required. Dark straw at 240 degrees Celsius, 465 degrees Fahrenheit, for milling cutters, drills, and taps. Brown at 255 degrees Celsius, 490 degrees Fahrenheit, for hammers and cold chisels that must endure repeated impact. Purple at 280 degrees Celsius, 540 degrees Fahrenheit, for screwdrivers and springs, where flexibility is more important than hardness. And blue at 300 degrees Celsius, 570 degrees Fahrenheit, for items that must be tough enough to bend without snapping. Beyond the hardening of steel, the technical prepper must master improvised foundry techniques to replace broken castings or create custom parts. When a gear cover on your Monarch breaks, or you need a custom bronze bushing, you cannot order it from a catalog. You must cast it. Building a backyard foundry begins with a furnace constructed from refractory materials, ideally a mix of fire clay, sand, and wood ash, which provides thermal insulation and resistance. For fuel, hardwood charcoal, and a forced air blower, even a manually cranked bellows, can easily reach the 660 degrees Celsius, 1220 degrees Fahrenheit, needed for aluminum, or the 900 degrees Celsius, plus required for brass and bronze. Green sand casting is the most resilient method for the survivalist, utilizing a mixture of fine silica sand and about 10% bentonite clay, which can be sourced from non-scented clay kitty litter. By packing this dampened sand around a wood pattern of the part you need, you create a mold that can withstand the molten metal. This local refining capability completes the cycle of industrial autonomy, allowing the 10EE to not only maintain itself, but to act as the primary node for a new, localized manufacturing hub. To reach the level of civilizational builder, one must also understand the chemistry of refractory linings for the forge and foundry. A high-performance improvised refractory can be made from 50% sand, 25% fire clay, and 25% perlite or crushed insulating brick. This mixture, when rammed into a steel bucket and allowed to cure slowly, can withstand the intense thermal cycles of melting iron. Without these materials, the furnace wall would simply melt along with the metal. Furthermore, the use of fluxes, such as borax for copper alloys or salt for aluminum, is essential to remove oxides and ensure a clean casting. This metallurgical mastery is the bridge between a pile of junk and a functional piece of machinery. The expansion of industrial survivalism must also include the precision of measurement. The precision of a machine is limited by the operator's ability to measure what has been made. Digital calipers and micrometers will fail when lithium batteries run out or their LCD circuits fry. The true arsenal of an industrial survivalist includes analog measuring tools and physical reference standards like gauge blocks. Vernier calipers, mechanical drum micrometers, and dial indicators maintain their functionality long after silicon chips have failed. Even optical comparators, which normally use filament lamps, can be adapted to use focused sunlight and mirrors to check complex thread profiles. Finally, a Monarch 10EE is useless without energy. The modern electrical grid is one of the most vulnerable systems to cascading collapse. The technical prepper must consider decentralized energy generation. Historically, workshops were powered by belts connected to water wheels or stationary steam engines. Adapting a 10EE to be driven by an alternative power source is a complex engineering project, but it is vital. Unlike CNC systems, which require a perfectly clean 60 Hz sine wave to avoid damaging processors, the DC motors of a manual lathe are tolerant of voltage fluctuations. This makes them ideal for power from improvised generators or battery banks charged by intermittent sources like wind or small-scale hydroelectric plants. History provides the most relevant case study for this industrial resilience: the special period in Cuba during the 1990s. With the collapse of the Soviet Union, the island lost 80% of its imports and faced a total breakdown of the supply chain. What emerged was a philosophy of technological disobedience, where citizens ignored the intended function of objects to meet survival needs. This era saw the rise of the culture of structural gambiarra, where fan motors were rewound for variable voltages and lunch trays became radio antennas. The Cuban army even published a manual titled "With Our Own Effort," teaching the population to manufacture fuel from biomass and repair household appliances. During the special period, machine shops equipped with manual machines became the nerve centers of communities. While automated machines sat idle for lack of electronic components, manual lathes continued to manufacture pistons, seals, and gears to keep Soviet-era tractors and buses moving. Cuban resilience proved that a society can survive a massive economic contraction if it maintains the capacity to manipulate metal manually and creatively. In summary, resilience is not a state, but a process of reducing dependencies. The value assigned to the Monarch 10EE is a practical recognition of physics and geopolitics. To ensure civilization can maintain its functional technological base, we must prioritize machines with mechanical transparency. Training must extend beyond machine use to encompass the synthesis of bio-based lubricants and the heat treatment of ferrous scrap. The true survival machine is the machinist's brain, yet the dematerialization of technical knowledge into automated software has created a generation of operators who do not understand the underlying mechanics. Manual machines will survive because they keep the human being as the master of the productive process, and not a mere spectator of an automation he can no longer repair. The Monarch 10EE remains the iron sentinel of a civilization that may, at any moment, need to rediscover how things are truly made. To further expand this industrial baseline, we must also consider the physics of precision scraping. When a lathe's bedways become worn, the machine loses its ability to maintain tolerance. In a survival world, you cannot ship the bed away for commercial grinding. You must use hand scrapers, tools made from old files, and a surface plate to manually remove thousandths of an inch from the iron, restoring the flat and parallel surfaces required for 0.01-inch precision. This is the ultimate test of the technical prepper: the ability to use a machine to repair itself, creating a closed loop of manufacturing that is entirely independent of the outside world. This level of dedication is what ensures that the light of industry never truly goes out.